So, welcome to this lecture on hardware security. So, today we shall be trying to understand about some new design techniques in perspective of the advanced encryption in perspective with the advanced encryption standard algorithm. So, to start with, let me go through the topics that we shall be covering in today's class. So, we shall be talking about AES implementation. We shall be talking with respect to the components of AES algorithm, which is essentially the mixed column operation and the sub box or the substitute box or the SBox implementation of AES. We shall be talking about we shall be trying to apply the techniques of isomorphism that which we learned in the last class, and try to see that how we can apply it for realizing a composite field AES. So, and finally, we shall be concluding with some quick look into one of the most efficient AES implementations, which is present in the modern day Intel machines in the form of a dedicated instruction for accelerating AES operations. So, to start with, we all know that cryptographic implementations are important, and we have got different paradigms for implementation. For example, we need fast designs. We need fast designs in the sense we need our designs to operate at higher clocks. We want to extract parallelism. That is one of the main reasons why we are looking into hardware design, and we also want that our design should support larger bandwidth. So, while this can be one category of objectives, you can also have another, or you can have other categories on the other end of the spectrum, where you need smaller designs. You need your designs to have low power, to should consume low power, and also take less area on silicon. So, therefore, this is also very important in certain contexts. For example, when you want your designs to operate on lightweight platforms, for example, like maybe your mobile phones or some resource constrained IoT node. So, therefore, we would probably need these kind of design paradigms, or various kind of design paradigms, and we need various kinds of design techniques for that. So, in one end we may require fast designs. On the other hand, the requirement may be of making designs which are lightweight and which essentially consume less energy and take less area, for example. So, therefore, depending upon the perspectives, your design choices may be different, and we will try to see some of them, some of these flavors when we talk about the AES algorithm in particular. So, therefore, but one thing is for sure, that we cannot compromise security, and as we will be seeing this in more and more details in our class, that just implementing with respect to these design choices may compromise security. So, therefore, at the end of the day, we have to also ensure that our designs are secure, and this we will be talking more and more details in during our course. So, to start with, we would like to discuss about some broad design strategies that we hardware designers adopt when we want our designs. For example, we may want to do our optimizations, which actually depend upon the mathematical formulations on which our ciphers are described. So, we would like to do something which is called as algorithmic optimizations, which are based on mathematical formulations that take advantage of the hardware platform. So, in order to to explain this part of the optimization, or these ways of optimization, I will be taking the example of isomorphism that which we discussed in the last classes, and we will try to see how we can adopt isomorphism to extract more compact designs of the AES algorithm. We will be trying to see how we can adopt it not only for components of the AES, but in general over the overall AES hardware. How we can make it consume less energy. How we can make it consume less resource. Okay. So, on the other hand, we also adopt architectural optimizations, where we try to exploit architectural techniques like pipelining and parallelism. So, these are of course techniques which we have learned in the context of computer architectures, and we also try to adopt them to get an end-to-end high throughput design. So, therefore, this is again taken from the same source which I cited in some of my previous old classes, where essentially this is just a summary of the various AES structures. So, therefore, if you remember that in AES, you can actually represent the AES algorithm by a 4x4 block, and each of these elements in this square matrix essentially are bytes. That means they are elements of GF 2 power of 8, that is Galois field 2 power of 8. And then what you do is that you basically pass them through several rounds. For example, in AES 128 you pass them through like 10 rounds, and each of the rounds are as follows. Like if you just to recapitulate and memorize, just remember what we already have discussed. So initially you do an XORing with a key, which is essentially the input key, and then you pass them through a certain sequence of steps, which are called the rounds of the AES algorithm. The first step is an SBox. So in the SBox you basically do a lookup. That means every byte is essentially substituted by another byte, and that is essentially denoted by this box, where you are basically having say like 16 SBoxes to get the substitution done. And after that you do a shift rows. In the shift row, the first row you don't do any shift. The second row you do a cyclic left shift by 1 position. The third row you do a cyclic left shift to the left by 2 positions or 2 byte positions, and in the final row you do a cyclic left shift by 3 byte positions. And once you have done that, after that we have this mixed column steps, which essentially takes each column and performs a matrix multiplication with a fixed matrix, as we have discussed in the previous classes, and then you get another column. So we basically do a column by column transformation, and finally the objective is that a combination of a shift row and the mixed column should essentially give me very fast diffusion in the cipher. Then I do an XORing with the round key, and finally I get the output of the first round, and then I pass this through, kind of iterate this process through say through 9 rounds in the case of AES 128, and then pass it through a final round. Now note, in the final round you have an SBox or substitution box layer, and you also have the shift rows, but you don't have the mixed columns. So the mixed columns is not present in the final round. Then you do an XORing with the final round key and you get the cipher. So while like AES 128 is just one parameter or one configuration of the AES algorithm, you may have other configurations. For example, like you may have AES 128, AES 192 or AES 256, depending upon which you change your number of rounds as well. Okay, so for example, in this case the number of rounds that you are doing is 9 plus 1, here you will be doing 11 plus 1, and here you will be doing 13 plus 1. So this is the number of intermediate rounds which you have in your cipher. So finally you get the cipher text, and that essentially is what the what an attacker should ideally see. That means the attacker should be able to see the cipher text and maybe the plain text, but from there would try to know what is the key. So that is the objective of what is called as cryptanalysis. So how the SBox is defined, or how the operations take place? Often in AES, right, we do the mathematics in GF 2 to the power of 8, as we have discussed. So therefore in GF 2 to the power of 8 or any extension field, we know that we need an irreducible polynomial. So the irreducible polynomial which is used for AES is as follows: x to the power of 8 plus x to the power of 4 plus x to the power of 3 plus x plus 1, and then you do your operations by doing modulo operations with this. As we have discussed that in AES, since it is based on composite fields, there are many opportunities for developing efficient implementations. In particular, just to remember the SBox, what we do in an SBox computation is that it is a byte by byte substitution, or it is a substitution operation. So therefore you take the byte, which is denoted here as A, and then you pass it through a series of transformations. So basically there are 2 transformations. The first is the finite field inverse. So you calculate a finite field inverse by performing a to the power of minus 1 modulo mx, where mx stands for this irreducible polynomial. Finally you get this result, which is denoted as GA, and then I do an affine transformation on GA. So that means like I take this matrix, I take this output of GA, which is denoted as as a vector from A7 to A1, or a polynomial. You can also think of that to be a polynomial, which should range from A7 to A0 actually, because this is an 8-bit element. So it is A0 to A7, which is 8 bits, and therefore this is an element in GF 2 to the power of 8. We then do an affine transformation, which means we basically multiply it by a fixed matrix and then add an vector, and finally get the result of my of the SBox. So therefore, right, and so this is like the broad constitution of the AES operation. Okay. And but there is also another very important layer which we have not really discussed in details, which is the key expansion. I will again not go into all the details on the key expansion, but rather just mention that in the key expansion you take an input key which is again 128 bits, and from there you try to develop the remaining round keys. So, for example, you develop 10 round keys when you are talking about AES 128. Likewise, for AES 192 and AES 256 you would require to generate 128 bit keys, or I mean every round will typically still have 128 bit keys, but in AES 192 or AES 256 your input key is of dimension 192 bits or 256 bits respectively. So, likewise the key scheduling is also takes account of these parameters. Okay, so now the question is, right, we would like to develop a hardware design for AES. So, what are the motivations of our hardware design? So, for example, right, one of the objectives could be that I would like my design to take less area. So, it should be like consume less. We should be able to implement it with lesser amount of gates, and therefore this particular how do we measure that whether our design is really consuming less area? We often measure it by what is called as gate equivalent, where we try to find out the number of 2 input NAND gates through which we can realize our design. So, that is often called as the gate equivalent, or abbreviated as GE. Likewise, we would also like to measure the throughput of our design, and therefore we would like to make our design having high throughput. So, I would like to increase the throughput of my design. And for AES, right, one of the objectives could be that I want a unified AES engine. That means one single hardware which will work both as an encryption as well as a decryption. Now, you should note here that the AES algorithm, right, is not symmetric in terms of encryption and decryption. That means the encryption process and the decryption process are distinct. So, how do you really make a single hardware which essentially functions both as an encryptor or as decryptor is a challenging proposition. Likewise, of course, we should be able to handle different key sizes, and this essentially is also an important could be an important design criteria, where a single device we should be able to support 128 bit keys, 192 bits or 256 bit keys. So, therefore, right, I mean there could be various such challenges for AES design. So, now I will try to look into like some of them during our discussions. So, I will start with the mixed columns. So, if you remember, in the mixed columns you essentially do a pre-matrix multiplication. That means you take basically an element in GF2 to the power of 8 and you pass it through a matrix. So, this is how you do a mixed column. So, therefore, here is a vector which is essentially nothing but a column of my state matrix. This element has got 32 bits, which means that each element is a 2 to the power of 8 or GF2 to the power of 8 element. So, what we do is that for the mixed column we pre-multiply it with this matrix. So, which is shown here as 2 1 1 1 3, 3 2 1 1, 1 3 2 1, 1 1 3 2. So, this matrix essentially is a 4 by 4 matrix, and each element is also an element in GF2 to the power of 8. So, when you are doing this multiplication of this matrix with this vector, remember that when you are multiplying say 2 with A3, okay, so when I am multiplying 2 with A3 or 1 with, or 3 with A0, okay, these multiplications are not integer multiplications, they are multiplications in GF2 to the power of 8. So, therefore, right, I would represent this 2 as a polynomial. So, this polynomial in GF2 to the power of 8 would be x. So, therefore, when I multiply x with say A3, A2, A1 and A0, then remember that when I am multiplying these 2 with A3, then 2 is represented as x, and likewise A3 will also have an 8-bit representation or a polynomial representation. So, when I multiply this with this, and whenever there is an overflow, that means the degree of the polynomial exceeds 8 or exceeds 7 rather, then I have to do a modulo operation. So, therefore, this modulo is again done by this mx polynomial, which is the irreducible polynomial which I use in context to AES algorithm. So, let us try to look into the mixed columns with this background. So, as I said that when you are calculating the mixed columns, then your input here is denoted as A, B, C, D. So, these are the 4 bytes of my column. So, I have got one column and I am processing it through this mixed column, and as I said that it is a 32-bit element, the column is a 32-bit element where each element is a byte. So, therefore, A is a byte, B is a byte, C is a byte and D is a byte. So, when I do this multiplication, then of course, like the first element is 2 into A plus 3 into B plus C plus D, and that essentially is my output element, which is capital A. Likewise, you have got capital B, capital C and capital D, but they are multiplied with different elements because each row, as we can see right in mixed columns, is a cyclic shift of the previous row. Okay. So, therefore, it's the same elements, but it is the arrangement is slightly different. So, finally, you get A, B, C and D, and again just what I said, like just to recapitulate this point, that when you are multiplying with 2, remember that 2 into A is not an integer multiplication, but rather is a multiplication in finite field, which means that I will do typically what I do in normal arithmetic, that is I will, if I want to multiply say this, remember that A you can also represent as a polynomial whose degree is 7, because it is an element of GF to the power of 8. So, when you multiply with 2, which essentially stands for x, then you are basically doing a cyclic left shift. Okay. So, therefore, x into the polynomial A, that means when I am calculating A into x, then I am doing a cyclic left shift of the polynomial A, okay, or you can think of like the bit representation of A. So, that is denoted here, like that when you are wanting to calculate 2 into x, you are basically doing a cyclic left shift of x. So, that is denoted here. But remember that is fine when the MSB of x is 0, okay. But when the MSB of x is 1, then basically there is an overflow, and therefore, once there is an overflow, you need to do a modulo reduction with your irreducible polynomial, and that is denoted here by this step, where you are basically doing an doing a modulo reduction with your irreducible polynomial for AES. So, therefore, right, I mean that gives you the how to compute 2x, and you know how to calculate 2x. Remember that when you want to calculate 3x or 3b, for example, and if you have got 2a and if you have got a, then you just need to add 2a with a to get 3a. Okay, that means you do not need to do an explicit multiplication with 3a, and that is why the mixed columns can be very efficiently implemented, and that is shown here in this diagram. What you do here is that you denote. Suppose my input is A, so I do it like multiplication with 2 as I have just now described. So, you calculate 2 into A, and likewise you can calculate 2 into B, but when you want, for example, in this case if you want 2A plus 3B plus C plus D, you can note that when I am doing the final XOR, then I am of course passing in 2A, because 2A is one of the components, but I also need 3B. So, I need to XOR with 3B, but how I am doing 3B is interesting. So, I am doing 2b, but I am not calculating 3b explicitly. So, I am just calculating 2b, and then I am XORing b with it. So, therefore, 2b XORed with b would stand for 3b, and therefore, I get 3b here without doing an explicit multiplication with 3. So, therefore, I have got 3b, and for c and d I just need to pass them, and therefore, c and d are XORed and passed. Finally, this XOR output will give me 2a plus 3b plus c plus d, or where the plus essentially is nothing but exclusive OR. So, likewise you can actually calculate the other elements in the column. For example, you can calculate A plus 2B plus 3C plus D. So, that is here, that is denoted here, where you are calculating these components, and likewise for the remaining elements in the you can calculate capital A, capital B, capital C and capital D in this fashion. So, note that when you are you can leave it at this point, but if you remember, like in your round you also need to add the key. Okay. So, therefore, that is denoted here by this layer. So, where key is again another byte. So, you can imagine that there are 4 bytes in the which you are taking from the key matrix, which is the round key matrix, and then you can actually XOR them after the output of this layer. So, therefore, after the mixed column you can do a separate dedicatedly different add round key. But here you can do a slight trick when you are like in particular going for FPGA implementations. Okay, and that is illustrated here. So, remember that as I told you that the lookup tables that you have in FPGAs often have got fixed input structure. That means they probably have got like 4 inputs or 6 inputs or so on, which means that if you are like not utilizing them properly, then there are a lot of wastages of the lookup tables. So, what you can observe here is that if you combine the key addition layer with the mixed column, then if you observe this XOR, for example, then this XOR has got 1, 2, 3 and 4 inputs. That means, if you do not use this key and if you combine it later, then you would probably require 2 equivalent lookup tables, but if you combine them and do it at one shot, then you require 1 single lookup table. So, therefore, you are basically doing the same operation, but you are saving on the resource that you need to make your design. Okay? And this is a small trick, but it can actually work nice, because remember that this process is being repeated for all the 4 columns, and therefore, right, the total amount of saving would be like always magnified, okay, and therefore it is a useful trick that you can try to adopt in your design. So the other important layer which is there in AES implementations is the SBox, okay. So as I said that SBox is nothing but a lookup table where you are basically substituting a byte with another byte. So one way of implementing them would be by using tables. So you can probably require a 256 byte table, and you can actually do your implementation by just writing, like just developing a memory based implementation. But this design would be slow due to what is called as the von Neumann bottleneck. So if you remember, I told this in the first class that like there is a big gap between the processing speed that your CPU enjoys and the memory access time, because the memory access time is inherently much slower compared to your CPU processing timing delay and other things. And that is why, right, what we have is what is called as a memory wall, and therefore, right, if you do your memory computations, then if you do the SBox in memory, then you are always kind of constrained by the memory access delay, and therefore your design becomes slow. More importantly, like you are using more resource because you are using the memory components, and therefore, right, while using SBoxes or using tables based SBoxes is probably more suited for software implementations. For hardware implementations, people probably try to develop logical equations. But at the same time, you also should kind of think that if you want to implement the AES SBox just by purely logic equations, then that also would consume large amount of resource, because each of these SBox elements, like if I take all the 8 bits of all the 8 output bits of SBox, then each of these output bits actually depends upon all the input bits of the SBox. Which means the one of the reasons why it is done is because you want to make your design nice. I mean, you want to make your SBox strong against standard cryptanalytic attacks, and therefore there are many design criteria which has led to the design of AES SBox, which is very nice, which essentially requires the AES SBox structure to be very complex, and therefore, right, if you would like to expand the output of the AES SBox in terms of its input, then you would require huge number of gates. You would require large number of components to do this design. Okay, for example, if you want to write the equations maybe on a piece of paper, then you would require a large amount of space to do that, and that means that your design is pretty complex. So therefore, right, I mean, what people try to develop is tricks or techniques for doing so. So for example, like if I go for a naive way or naive method of implementing an SBox, I can actually try to adopt what we have already studied is the, I mean, we can also go for these approaches where you try to apply maybe the Euclidean algorithm or the extended Euclidean algorithm for computing the AES output or the SBox output, but then you would require large amount of clock cycles for doing so. Okay, so therefore I can of course compute the inverse of x in GF to the power of 8 using the extended Euclidean algorithm and then apply the affine transformation. But if I do this in this process, then several clock cycles will be required to get the output of a single SBox. Okay, and imagine that you have to do this for maybe 16 SBoxes. Of course, you can do them in parallel, but then you would require a large amount of resource. But there is a very interesting trick where we try to apply the principles of isomorphism, and this is an example of algorithmic optimization, okay, as we have defined, where we try to apply the techniques of isomorphisms and use a principle of what are called as composite fields. So as we have discussed, like composite fields are fields of the form of GF to the power of n whole power of m. Okay, so if I try to apply composite fields and apply the principle that all the composite fields are isomorphic if they are properly designed, then I can actually make very compact designs of the AES SBox, which will probably require less than 100 gates or maybe around 100 gates, and we can essentially do the entire thing using a combinational circuit. That means I can do it without expending clock cycles to get the output of the SBox. Okay. So therefore, let me take an example, or let us try to example motivate why we need to go into this. Okay, or try to understand the savings that we can essentially get out of this technique. So this is to remember that in AES we use the binary finite field, which is GF to the power of 8, and my modular reduction polynomial or the irreducible polynomial is as x to the power of 8 plus x to the power of 4 plus x to the power of 3 plus x plus 1. So now we will use this principle, that is GF to the power of 8 can also alternatively be represented by this composite field structure, which is GF to the power of 4 whole power of 2. or even you can break down GF to power of 4 further, and then you can also have fields like GF2 squared power of 2 power of 2. So even that is isomorphic. Okay. So that means now I can do my designs in a much smaller field. For example, if I want to calculate an inverse or do an inverse in GF2 to the power of 8, then I can transform my element into GF2 to the power of 4 squared, which is this, and then do my inverse computation in GF2 to the power of 4. So what I can do is that I can, like one way of doing this implementation is that I can just have a table based inverse computation for GF2 to the power of 4, and that would be much more compact than doing an inverse in GF2 to the power of 8. Okay, and therefore, right, I can have an overall compact design to get the output of GF2 to the power of 8 inverse. Okay, so therefore I will implement this GF2 to the power of 4 in a table based manner, and then use logical equations to derive the output in GF2 to the power of 8, okay, or GF2 to the power of 4 square. So this transformation from GF2 to the power of 8 to GF2 to the power of 4 square and vice versa, for this I need a conversion matrix, and as we have discussed in the previous class, there are different class of algorithms through which we can get these transformations being computed. So therefore, right, if you are able to do that, then what you will do is as follows. You will take x here, and then you will map this x to an element in the composite field. That means, remember that x was in GF2 power of 8. So now you will map this GF2 power of 8 into GF2 to the power of 4 square, okay, and then do the inverse computation in GF2 to the power of 4 square. That means this inversion will be calculated in GF2 to the power of 4 square, and then you will do a reverse map to bring the result back to GF2 to the power of 8, and then you can do an affine transformation. Okay. So remember that affine transformation has to be done, because you finally want that your algorithm should be producing the correct result as per the specification of AES. Okay. So then you can also do a very simple trick where this reverse map, remember, can also be remember that the map and the reverse map, based on the final algorithm that I discussed in the last class, can be represented by a linear matrix, which is a 0-1 linear matrix, right. So therefore, what I can try to do is I can try to combine the inverse map matrix with the affine transformation matrix. Remember that these are two matrix operations, and therefore I can combine them, and I can get a one single matrix to do this transformation. Okay, and that probably would make my design more compact than having two independent maps. Okay, like the reverse map followed by the affine map. We can try to combine them into one single map. Okay, and that can save some gates. So how we transform this element from GF2 to the power of 8 to this field GF2 to the power of 2, I will not go in details here, because that is what we essentially covered in details in the last class, but maybe you can go through this thesis, and it's a very nice reference for this kind of discussions. And just remind you that one way of doing that is you just map the 0 of this element to the 0 of the the 0 of GF2 to the power of 8 to the 0 of the composite field, and then find alpha, which is a primitive root of the field GF2 to the power of 8. You find beta, which is a primitive root of the GF2 power of 2, and then you develop this map. So therefore, you just try to map alpha to beta, you try to map alpha squared to beta squared, try to map alpha cube to beta cube, and so on. So therefore, you can essentially have a nice map between all these 256 elements which are there in GF2 to the power of 8 as well as in GF2 to the power of 2, because they are equinumerous. Both of them have got the same number of elements, only the way you are doing the computation is different. So therefore, when you are doing isomorphism, what you can do is you can actually calculate, you can perform a multiplication in the transform field, and then you can apply the reverse transformation to get the result in the original field. That is what we have discussed in the previous class. But what we are trying to take advantage of is that the computations, that means the multiplications and the inverse computations in the composite field should be more efficient than in the original field, which is GF2 power of 8. Okay. So let us see that what are the benefits of doing this, and here is a simple illustration of how or what are the benefits of that. For example, I am not going. So let us not try to be bothered about this architecture right now, but just try to see the benefits. Okay. For example, when you are, for example, measuring the gate counts for composite SBox implementations. So here are some figures which have been provided to us. Okay. So when you are calculating the SBox or composite SBox implementation, then you can see the number of gates which are required to do this design. Okay. So, for example, the number of XORs is something like 80, the number of NAND gates is 34, number of NOR gates is 666, total number of gates in terms of NAND. So, this is the what is called as the gate equivalent when you are representing the entire gate requirement in terms of two input NAND gates. And for standard cell libraries, it turns out to be 180, which is like around 100 to 200 gates you can do this design. Okay. So, so likewise, right, you can actually also try to look into this, that suppose I want like to do this design rather than standard cells, but I would like to do this design on FPGAs. Okay. So, here you can see that for a composite field based AES SBox implementation, the number of slice requirements is 30 and the critical path of my design is 18.3 nanoseconds and the gate count is something like 312. Okay. So, if you compare this with a pure lookup table based implementation, you can see that the number of slices which is required is significantly reduced. It was previously 64 in a lookup table based implementation, but now it has been reduced to 30, okay, which is almost like half. Now, if you compare with of course, there is a penalty which you pay for that, and like when you are doing your computations in logical circuits, then of course you can expect that the critical path of your design will increase. Okay. And that is shown here by these figures, where you can see that the critical path increases from 11.9 nanoseconds to 18.3 nanoseconds. Okay. So, but at the same time, right, also keep in mind that like you also have like when you are implementing in lookup table, then and if you are, for example, going for a dedicated memory based implementation, then there is a memory access time which would also try to like get accounted into this. Okay. So therefore, right, I mean, of course, I mean, you can say that like there is an increase in the critical path delay, but like I believe that we should be able to appreciate the fact that there is a significant amount of reduction in terms of the number of gates which are required to do this design. Okay. For example, the gate count here has diminished from say 1128 to only 312. Okay. So that's a phenomenal amount of decrease in terms of gate counts. Okay. And therefore, right, if that happens, right, then you can actually go for like parallel implementations of the AES SBox to alleviate the throughput issues, and you can essentially get a very nice trade-off between like throughput as well as area when you go for composite field implementations. Okay, and that shows like the merit of composite field implementations. So therefore, right, we will stop here, and rather we will discuss in our next class on like how this architecture comes and how we can actually use composite fields to get an overall architecture for the SBox. So we'll start from there and again go into the mixed columns and then try to see the overall picture. Okay. So thank you for your attention.